Hey everyone, and welcome. Today we're going to jump into a concept that is honestly a cornerstone of smart automation and PLC programming. It's called edge detection. And it's basically the secret sauce that lets a machine react not just to a signal, but to the exact instant that signal changes. So how does it all work? Well, let's dive in.
So let's start with a basic puzzle. You press a button, right? The input to the PLC turns on. As long as you hold it, it stays on. You let go, it turns off. Simple. But what if you need something to happen only at the precise moment you press it and not happen over and over again while you're holding it down? How does the controller tell the difference between a continuous on state and a single momentary action?
And the answer, my friends, is edge detection. It's this brilliant programming tool that lets you generate a single lightning-fast pulse. And I mean fast. It only lasts for one scan cycle of the PLC. So it's not about the signal just being on. It's about capturing that split-second moment where the signal state actually changes. It's all about that timing.
Okay, so there are really two main flavors of edge detection. We're going to start with the first one, the positive edge. You might also hear it called a rising edge, or in the programming world, a P trigger.
So what exactly is a positive edge trigger? Well, think of it like a lookout. It's constantly watching an input. And the very instant that input flips from off, or a 0, to on, or a 1, bam, the P trigger fires. But here's the really crucial part. Its output is only true for one single scan of the PLC's program. It's an incredibly brief and super precise event. So, how does the PLC actually pull this off? It's pretty clever, really. It uses a little bit of memory. On its first scan, it looks at the input and thinks, okay, it's off, it's a 0, and it stores that little piece of information. On the very next scan, we're talking microseconds later, it looks again and goes, whoa, hang on, now it's on, it's a 1. Because it remembers what it was before, it can see that change from 0 to 1 and says, aha, that's a rising edge. Time to trigger that pulse. You know, the easiest way to remember this is to connect it to something physical. The positive edge is all about the beginning of an action. It's the press. That exact moment your finger makes contact and the switch closes, that's your rising edge. All right, so if we can detect a signal rising, it only makes sense that we can also detect it when it's falling, right? So let's flip the coin and look at the other side, the negative edge. The negative edge, or N trigger, is pretty much the perfect mirror image of the positive edge. Instead of looking for a signal to turn on, it's waiting for a signal that's already on to finally turn off. It's looking for that transition from a 1 back down to a 0. And just like its counterpart, the output is only true for that one single super brief scan cycle. The logic is exactly the same as before, just in reverse. The PLC is scanning the input, it sees, okay, the input is on, it's a 1. It remembers that. On the next scan, it checks again and finds, oh, now it's off, a 0. By comparing that new state to the one it remembered, it spots the change, and that's when it triggers the N trigger pulse. And this just beautifully completes the entire action, doesn't it? If the positive edge is the press, then the negative edge has to be the release. It captures that exact moment you lift your finger off the button and the signal disappears. Putting them side by side like this just makes it crystal clear. You've got the positive edge looking for that off to on transition, that's your press. And on the other side, you've got the negative edge looking for the on to off transition, your release. Both give you that single momentary pulse, which gives you incredibly precise control over both the start and the end of any action. Now, all this theory is great, but let's see why this is so incredibly useful out in the real world. We're going to look at a classic programming challenge that, honestly, would be almost impossible to solve cleanly without using edge detection. This puzzle is awesome because it really forces you to think about not just if a button is pressed, but how many times it's been pressed. This is exactly where the power of capturing that one single moment of change really shines. So let's break down the rules of the game. You've got just one button to control the whole show. The very first time you press it, motor 1 needs to turn on. The second time you press that exact same button, motor 2 starts up, but motor 1 has to keep running. And then, on the third press, everything shuts down. After that, the sequence resets and it's ready to go all over again. So, how do you make the PLC count those separate, distinct presses? And this is the line that just sums it all up perfectly. Whether you're counting button presses, latching a circuit, or just triggering a one-time event, the real power of edge detection comes from this single idea. It doesn't care about the state, it cares about the transition. It works only in that brief, powerful moment of change. And that brings us to our final thought. With everything we've just talked about, think about that challenge again. How would you use those positive edge triggers, maybe with a counter, to tell the difference between the first press, the second, and the third? That right there is the key to unlocking this puzzle and so many other real-world